Dear students, we are discussing the concept of ring and we have discussed quite a few examples of rings. Let's consider one more example. We know that Z, the set of integers. This is a ring. Now consider this particular set. We multiply each element of Z with 2. So this will become minus 6 minus 4 minus 2 0 2 4 6 and so on, and we denote it by 2Z. And note that this set is closed under addition. We note that first of all 2Z is closed under binary operation addition. Secondly, addition is associative. Addition is associative in 2Z. Further, 0 is additive identity. Additive identity in 2Z. Further, each element has additive inverse in 2Z. Each element of 2Z has additive inverse For example, 6 and minus 6 are inverses to each other. 4 and minus 4 are inverses to each other. 2 and minus 2 are inverses to each other, and 0 is inverse of 0 with respect to addition. So each element of 2Z has additive inverse. And finally, addition is commutative in 2Z. So hence 2Z is a abelian group under addition. We also note that 2Z is closed under multiplication, because when you will multiply an even number with an even number, result will be an even number. Minus 4 into minus 2 will be equal to plus 8. Plus 8 is in this set. 2 multiplied with minus 2 is equal to minus 4. Minus 4 is here in this set. So 2Z is closed under multiplication. Is closed under multiplication. And further, multiplication is associative in 2Z. multiplication is associative, in 2z. Reason is because multiplication is associative in z and the elements of 2z are in 2z is subset of z in fact. Therefore multiplication is associative in 2z as well. So multiplication is associative in 2z. And thirdly, multiplication distributes over addition. Multiplication distributes over addition from both sides, from left hand side as well as from right hand side, from both sides. The reason is again same, because multiplication distributes over addition in z, so it will distribute over, multiplication will distribute over addition in 2z as well. So all these conditions give us that 2z is a ring. Therefore 2z is a ring, because 2z satisfies all the conditions for being ring. So having said that, similarly we note that we can see that 3z, 4z and so on are rings as well. In fact, in general, nz is a ring for each natural number n, for each n belonging to set of natural numbers. So we got another class of rings. So 2z is ring, 3z is ring, 4z is ring, 5z is ring, and so on. So now we have quite a good number of examples before us. Based on these examples, let's make few more definitions. Let's discuss about rings which satisfy commutative property for multiplication. So let's properly, formally define this thing, commutative ring. So definition goes as follows. Let R be a ring. Let R be a ring. Please note that when we say that R is a ring, it is understood that there are two binary operations. One is denoted by the sign plus, we call it addition, and second we mostly denote it by juxtaposition and we call it multiplication. Under addition, R is an abelian group and identity element is denoted by 0. And under multiplication, multiplication R is closed and multiplication is associative. And then multiplication distributes over addition. So when we say that R is a ring, we understand that there are two binary operations. addition and multiplication with details I have just narrated. So let R be a ring. Then R is called commutative ring. Is called commutative ring if multiplication is commutative. Note that in definition of ring we have required that addition is commutative, but on multiplication there is no such condition. But if multiplication also happens to be commutative, then the ring is called commutative ring. So then R is called commutative ring if A multiplied with B is equal to B multiplied with A for all A, B belonging to R. So if multiplication is also commutative, then the ring is called commutative ring. So let's see examples of commutative rings. Z, the ring of integers, or the ring of real numbers. When we write R in this way, this means this is a symbol for ring. And when we write R in this way, this means the ring of real numbers. Let me qualify it, the ring of real numbers. So Z, or the ring of real numbers, Q, the ring of rational numbers. You very well understand this notation. C, the ring of complex numbers. Z6, you know that this is ring under binary operation, addition modulo 6 and multiplication modulo 6. We have discussed this example in our previous sessions. Z7, and in general Zn are commutative rings. So these are commutative rings. We have more examples. Ring of quadratic integers is a commutative ring. A ring of quadratic integers is commutative ring. Then the ring of Gaussian integers is commutative ring. So the ring of Gaussian integers is commutative ring. And then the rings we have just discussed, that is 2Z, 3Z, so on up to, and in general NZ. These, all of these are commutative rings. To understand this concept in better way, it is good if we discuss examples of non-commutative rings as well. So let's see examples of non-commutative rings. Those rings which do not satisfy this particular condition. So examples of non-commutative rings. So first of all, we note that you must be remembering this particular ring M2. We discussed this ring as this is ring of square matrices of order 2 by 2. So A11, A12, A21, A22, such that Aij's are real numbers. Aij's are real numbers. So this particular ring, we have proved that this is a ring, and this is a non-commutative ring. Is non-commutative ring because multiplication of matrices is non-commutative, because AB is not equal to BA in general. For AB belonging to M2. Since multiplication of matrices is not necessarily commutative, therefore this particular ring is non-commutative ring. We will discuss this ring in more detail in more general setup. So second example we have discussed of non-commutative ring is ring of n by n square matrices. This is an example or a particular case of the example we are going to discuss now. So Mn is equal to Aij such that I is equal to 1, 2, so on up to n. J is equal to 1, 2, so on up to n, and Aij are real numbers. And Aij are real numbers. Square matrices of order n by n with real entries, and Aij are real numbers. So we have discussed earlier that this is a ring. So this is a non-commutative ring. The reason is same, because if we multiply two matrices A and B and A by changing the order, their product may not be equal, is not equal in general. For AB belonging to Mn. So ring of square matrices of order n by n is a non-commutative ring as well. So this is our second example of non-commutative ring. We come to next example. And we know that ring of Hamilton's quaternions. In fact, Hamilton's quaternions form a ring, and this is non-commutative ring as well, for the reason I will just explain. So ring of Hamilton's quaternions is non-commutative ring because we know that if we multiply I with j, we obtain k, and if we multiply j with k, if we multiply j with I, then we obtain minus k, because ij is not equal to ji. Similarly, jk is not equal to kj, and ki is not equal to ik. So the ring of Hamilton's quaternions is non-commutative. In general, when you multiply two quaternions, result may not be same if you multiply them by changing the order. So, and you can see that from these conditions as well. So ring of Hamilton's quaternions is a non-commutative ring. So these are examples of non-commutative rings. So having said that, let's have a simple note by noting that we note that if we consider only zero element, then this is a ring as well, is a ring, and this is called trivial ring, called trivial ring. I just want to note that in our study of rings, mostly we will be concerned with non-trivial rings. So let me note that in our study of rings, whenever we say ring, we mention ring, we will always mean non-trivial ring. We will always mean non-trivial ring, unless mentioned otherwise. So I simply want to make it clear that whenever we will say ring, we will mean a ring other than this particular non-trivial ring. And if we needed this particular ring, then we will mention it that this is the ring we are going to consider now. In fact, it will make our life easier, because otherwise we will have to say again and again non-trivial ring, non-trivial ring. So we just decide in the beginning that whenever we say ring, we will mean non-trivial ring. And if we needed this particular ring, we will mention it. So having said that, Let's come to another observation, and that observation relates with the existence of multiplicative identity in the ring. Note that every ring has additive identity, and that is 0. But a ring may not have multiplicative identity in it. I give you example. For example, this ring 2Z, this does not contain multiplicative identity 1. Similarly, 3Z will not contain multiplicative identity 1, and so on. So a ring may or may not contain multiplicative identity. So if a ring contains multiplicative identity, we call it ring with identity. For example, the ring of real numbers contains multiplicative identity 1. So the ring of real numbers is ring with identity. So let's have formal definition. So this is definition of ring with identity. When we say ring with identity, we mean ring with multiplicative identity. So please remember that. So a ring R is called ring with identity if there exists, we denote multiplicative identity by 1. If there exists 1 belonging to R, and let's qualify what does this mean, such that 1 multiplied with A is equal to A multiplied with 1. Let's put dot here because most we don't put it, but sometimes it seems necessary. Such that 1 multiplied with A is equal to A multiplied with 1 is equal to A, and this is for all A belonging to R. So if multiplicative identity exists in the ring, then that ring is called ring with identity. So let's see examples. Z, the ring of integers, or the ring of real numbers. Q, the ring of rational numbers. C, the ring of complex numbers. All these rings are rings with identity. And similarly, our ring M2, we have discussed before. Mn, we have discussed before. Even our ring of Hamilton quaternions, H, the ring of Hamilton quaternions. And the ring of quadratic integers, the ring of quadratic integers. And even Z6, Z7, and Zn in general. All these rings are rings with identity. rings with identity. Let's write identities anyway. So each of these rings have multiplicative identity in them. Z, 1 is there. R, 1 is there. Q, 1 is there. C, 1 plus iota 0. M2, 1, 0, 0, 1, and so on. So all these rings are rings with identity. So examples of rings without identity, let's see those examples as well. Examples of rings without identity. So examples of rings without identities. And we know that 2Z, 3Z, 4Z, and so on up to NZ. NZ, we must note that where n is greater than or equal to 2. So these rings are rings without identity because multiplicative identity is not present in 2Z, not present in 3Z, not present in 4Z, not present in NZ if n is greater than or equal to 2. So these are rings without identity. And I mention it again, when we say identity, we mean identity with respect to multiplication, multiplicative identity. So these are rings without identities. So next we discuss a ring in detail, and that is matrix ring, ring of matrices, ring of square matrices in fact. So matrix ring. In fact, note that when we discussed two examples earlier about rings of matrices, we considered entries from the ring of real numbers. But in general, we can take entries of matrices from any ring. So let me first mention that we have already discussed rings. We have already discussed rings. M2, this was ring of square matrices. Let me write it in this way, Aij, such that I is equal to 1, 2 and j is equal to 1, 2. And Aij are real numbers. So this is the one ring we have already discussed. This is a non-commutative ring with identity. And Mn. When we were discussing ring with identity, yes, we have mentioned M2 and Mn are rings with identity. anyway. And Mn is equal to Aij such that I is equal to 1, 2, so on up to n. J is equal to 1, 2, so on up to n. And Aij are real numbers. So we have already discussed these two rings, and these are the rings of matrices such that entries of the matrices are from R. So these are the rings. Rings such that entries of matrices are elements of R, the ring of real numbers. In fact, we can consider square matrices with entries from any ring with identity, in fact, because you need to have identity, because square matrices have two identity matrix in order to have an identity in that. So we may take entries of matrices. So we may take entries of matrices from any ring R, from any ring R with identity. So it is not necessary that our matrix should have entries from ring of real numbers. We may take any ring R with identity to have our matrices entries from. So let's consider a ring R. So let R be a ring. So let R be a ring with identity. Then now this is just a notation. Mn mean matrices of order n by n, where n is a natural number, and just I put in bracket capital R. This means that entries of these matrices are going to be from this particular ring R. So then MNR is equal to square matrices Aij. Let's denote this matrix by A. A is equal to Aij such that I is equal to 1, 2, so on up to n. J is equal to 1, 2, so on up to n, and Aij belong to R. So this is set of square matrices of order n by n with entries from the ring R. Then M and R, let me clear it, which is set of square matrices of order n by n having entries from ring R. Then this particular set M N R is a ring. In fact, this is a ring with identity. Ring with identity, and it has quite important role in mathematics, and this ring is called full n by n matrix ring, and is called full n by n matrix ring. We call it full for the reason that to mention that this ring contains all the square matrices of order n by n. Just to avoid the ambiguity of non-singular matrices. We are not talking about non-singular matrices only. We are talking about all the matrices of order n by n. So all the set of all the matrices of order n by n with entries from ring R is a ring, and this ring is called full n by n matrix ring. So we will prove it formally. Let's prove it. So proof. This proof are that M and R is a ring with identity. So we give a formal proof, in fact just hints for that formal proof. So this is a ring with identity. So let's discuss the proof. For proof, first of all, we have to define addition and satisfy all the conditions for this particular set being an abelian group under that operation. So first of all, for addition, so for addition we take two matrices and we define what addition is. So let these two matrices A and B belong to this particular set. We have denoted by M and R, and we clearly mention what A is. So let A is equal to Aij and B is equal to Bij. And then we define and you are quite familiar with this particular definition of addition of two matrices. If we have got matrices of same order, then their sum is defined by adding the corresponding entries of both matrices. So A plus B is equal to Aij matrix plus Bij matrix, and this matrix is obtained by adding the corresponding entries. So entry of ith row and jth column of matrix A plus entry of ith row and jth column of matrix B. So adding the corresponding entries, we obtain a matrix, and this matrix is again of order n by n, therefore belongs to this particular set MNR. So this is the way we define addition. So therefore it is easy to see that MNR is closed under addition. Under addition, addition means the addition we have defined, which we have defined. So this is the way we define addition. Secondly, we have to, addition is associative. So associativity of addition. It is very simple. Let's do it in detail. So let A, B, C be three matrices with entries from the ring R belong to MNR. Let's write these matrices clearly, where matrix A is equal to Aij, matrix B is Bij, and matrix C is Cij. So these are the three matrices with entries from the ring R. Then A plus B plus C. Let's see what does this mean. A plus B plus C is equal to matrix A is Aij, and then plus matrix B is Bij, and then plus C, matrix C is Cij. And this is equal to, this is matrix Aij, and then plus, now apply definition of addition of two matrices. We have to add the corresponding entries. So sum of these two matrices will be equal to this particular matrix Bij plus Cij, by using this definition. And now we add these two matrices with each other. This is equal to, we add corresponding entries. So entry ijth entry of this matrix is Aij, and then plus ijth entry of this matrix is this particular thing, plus we put it in bracket Bij plus Cij, and this is equal to, now since Aij, Bij, Cij are entries from a ring R, and addition is associative in every ring, therefore we can use associative law of addition. So this is equal to Aij plus Bij, associative law, and then plus Cij, and this is equal to, now use definition of addition of matrices as we have defined above. So this is equal to this matrix Aij plus Bij, and then plus this matrix Cij. and this is equal to, this is sum of two matrices A and B, Aij and Bij, so this is equal to sum of these two matrices Aij and Bij, and then plus this matrix Cij, and this is equal to A plus B, and then plus C. So we know that A plus B plus C is equal to A plus B plus C. Therefore, addition is associative in this particular set. Therefore, addition is associative in this particular set MNR. So we have proved that addition is associative in the set MNR. So next we have to see what is additive identity. Additive identity. So additive identity, and you know that what additive identity is going to be. This is going to be a matrix of order n by n having each entry is equal to 0. So additive identity in MNR is the matrix of order n by n having each entry equal to 0. Each entry equal to 0. So we can just define it, that is, this is our additive identity. Additive identity is going to be this particular matrix. Let's write it as Xij, where Xij is equal to 0 for every I 1, 2, so on up to n, and for every j 1, 2, so on up to n. So this will be a matrix having each entry equal to 0, and this can be very easily checked that this is additive identity. You can check it very easily on your own, because when you add two matrices such that one matrix has each entry equal to 0, and second matrix, any matrix you like, then the result will be the matrix you have added with this 0 matrix. You can check it very easily on your own. So this is additive identity. Next we come to additive inverses. Additive inverses. So let A belong to Mn, or where A is equal to this particular matrix Aij, then the matrix, and you know this matrix very well, all you have to do is just change the sign of each entry of this matrix A. So this is the matrix we are talking about. Change the sign of each entry. So mine is Aij. And we denote this matrix by minus A. Then this particular matrix which belongs to this particular set M or R. So this matrix is such that if you add A with this matrix minus A, or you add minus A with this matrix A, result will be equal to this. So result will be equal to 0 matrix, and you can check it very easily. You know it very well from your intermediate. So therefore minus A is additive inverse of A. So we have discussed that additive identity exists in MNR. So this is about additive inverse exists in MNR for every element. So therefore additive inverses exist in this particular set MNR. So this is about inverses. So having done that, it is clear that MNR is a group under addition. Therefore MNR is a group under addition. Finally, we have to mention that, or finally we have to establish that this group is a abelian group under addition. So finally, to see that addition is commutative, let's take two matrices. Let A, B belong to M and R, where A is equal to this matrix Aij and B is equal to this matrix Bij as usual. Then let's add matrix A with matrix B first. Then A plus B is equal to, we are going to add matrix A with matrix B, and matrix A is Aij plus matrix B is Bij, and this is equal to, by our definition of addition, this is Aij plus Bij, and this is equal to, you know that in ring R addition is commutative, so Aij plus Bij can be written as Bij plus Aij. Now again apply the definition of addition of matrices. So this is equal to matrix Bij plus matrix Aij, and this is equal to B plus A. So we have established that A plus B is equal to B plus A. Therefore addition is commutative. Therefore addition is commutative in MNR R, and therefore MNR is an abelian group under addition. Is abelian group under addition. So we have established about addition that MNR is abelian group under addition. Now we come to multiplication. Secondly, we come to multiplication. First, we have to define the multiplication as we did in case of addition. So let's take two matrices or two elements of M and R. So let AB belong to M and R, where A is equal to Aij and B is equal to Bij. Then we define multiplication of matrices. Product of these two matrices A and B is defined as now recall that the way we define multiplication of two matrices, what we do is that we take ith row of matrix A and multiply each entry of ith row of A with corresponding entries of jth column of B, and we get ijth entry of product AB. Let me write it here. What we do is we take ith row of matrix A and multiply each entry of this ith row with corresponding entry of jth column of matrix B. So jth column of matrix B, jth column. We multiply and then we add. So this is the way we can do it here. AI lambda and B lambda j, and we give summation. Lambda varies from 1 to n. So this is ijth entry, and we give it the symbol of matrix. So this is the way we define product of two matrices, and you can see that since A matrix is of order n by n, B is of order n by n, so this matrix will be again of order n by n. So this belongs to M and R. In fact, this is the definition you have studied at your intermediate and then at your BSc as well. So therefore, MN R is closed under multiplication. We have defined closed under multiplication. So this was multiplication is closed. And secondly, we have to see that multiplication is associative. So associativity of multiplication. So associativity. So for associativity, we need three matrices. So let A, B, and C belong to this particular set M and R, where A is equal to Aij, B is equal to Bij, and C is equal to Cij. Then if we multiply A with B and multiply the resulting matrix with C, or we multiply B with C and multiply the resulting matrix from left hand side with A, then these two results have to be equal. So this is what we have to establish. And very simple to establish this result. I will simply write in the form of hints, because you can do it very easily, details on your own. So I will just write hints. So let's see, what we have to do is that, let's see what A multiplied with B multiplied with C is going to be. So note that B multiplied with C is going to be. What we are going to do is we are going to add, in order to obtain ijth entry of this particular product, we are going to multiply ith row of AB with jth column of C, corresponding entries in fact, and then we are going to add them with each other. So just try to understand this particular thing. AI lambda, B lambda, I am going to write here mu, B lambda mu, and then I am going to take summation over lambda varies from 1 to n, and I am going to multiply this particular term with C mu j, and then I am going to take summation over mu varies from 1 to n, and this is the matrix we see as product of the three matrices. Note that this is summation. Here summation is over lambda, and I and mu, these are free here, and then this is summation over mu, and you can see that this is in fact we are multiplying ith row of AB. This is entries of ith row of AB with jth column of C. Jth column of C. Note that J, we are not giving summation over J. So this is jth column of C, and this is ith row of AB. This is ith row of AB, and this is jth column of C. If you pay a little attention, you can see it very easily. In fact, there is no summation over I, so this is ith row of A. There is no summation over J, this is jth row of C. So we are multiplying ith row entries of ith row of AB with corresponding entries of jth column of C, and then we are adding them with each other. So just pay a little bit attention and you will be able to see that. And this is equal to sigma mu varies from 1 to n. Sigma lambda varies from 1 to n. AI lambda, B lambda mu multiplied with C mu j. And now use associativity of multiplication of ring R, because in ring R multiplication is associative, so we can use associativity. So this is equal to sigma mu varies from 1 to n, sigma lambda varies from 1 to n, and then AI lambda multiplied with B lambda mu C mu j, associativity. And this is equal to, now just note that mu is only in these two terms. So effect of mu varies from 1 to n. This will affect only on this part of this expression, only on this part of this expression. So you can write it as, this is equal to sigma lambda varies from 1 to n, AI lambda, and then sigma mu varies from 1 to n, B lambda mu C mu j. And this is equal to, you can see it very easily now. This is ith row of A, this one, ith row of A. And this is jth column of BC, jth column of BC, ith row of A, jth column of BC. So this is equal to ABC. So ABC is equal to ABC. So therefore, multiplication is associative in MNR. So having done that, multiplication is associative. We have completed the conditions for multiplication. Now we come to distributive law. Thirdly, we come to distributive laws. So for distributive laws, we need three matrices. So let A, B, C belong to MNR, and let's write in detail where A is equal to AIJ, B is equal to BIJ, and C is equal to CIJ. We shall prove that if we add B with C, and multiply with A, result has to be equal to AB plus AC. This is left distributive law. And if we add B with C and multiply with A from the right hand side, this has to be equal to BA plus CA. This is the right distributive law. So this is what we have to establish. So in order to establish that, let me write, in fact, this will contain all the details, but let me put it as hints. So for the first law, let's take A multiplied with B plus C, A multiplied with B plus C, and this is equal to, now we have to be very careful in writing that. We are going to write ijth entry of A multiplied with B plus C. So first of all, let's take jth column. We are going to multiply ith row of A with jth column of B plus C. So jth column of B plus C is going to be B lambda J, entries of jth column of B added with entries of jth column of C, C lambda J. So this is sum of entries of jth column of B with corresponding entries of jth column of C. So we are going to multiply it with ith row of A from left hand side. So this is AI lambda. So this is ith row of A, and then we are going to take summation over lambda varies from 1 to n. So this is what A multiplied with B plus C is going to be, and this is equal to sigma lambda varies from 1 to n. Since multiplication is distributive over addition in the ring R, so this can be written as AI lambda B lambda J plus AI lambda C lambda J. And now apply the definition of sum of two matrices. So this can be written as sigma lambda varies from 1 to n, AI lambda B lambda J B lambda J. This matrix plus this matrix, sigma lambda varies from 1 to n, AI lambda C lambda J, and this is equal to, you can see that this ijth entry is in fact of A multiplied with B, and this is of A multiplied with C according to our definition of multiplication of matrices. AB matrix, product of AB, and this is product of AC. So A multiplied with B plus C is equal to AB multiplied AB plus AC. Similarly, we can show that Similarly, we can show that B plus C multiplied with A is equal to BA plus CA. So therefore, multiplication is distributive over addition from both sides. Therefore, distributive laws hold. Distributive laws hold. And therefore, M and R, that is the set of square matrices of order n by n with entries from the ring R is a ring. So far we have established that this is a ring. So having done that, finally we note that MNR is a ring with identity. Finally we note that MNR is a ring with identity. Is a ring. Identity means multiplicative identity. Is a ring with identity. We mention what identity is going to be, where let's represent it by capital I. Capital I is equal to this particular matrix. Let's write it as Eij, and in fact this matrix is going to be, let me explain it here. This is going to be 1 0 so on up to 0, 0 1 so on up to 0, so on up to 0 0 so on up to 1. And you know this matrix. In fact, this is a matrix which has 1 at diagonal and 0 elsewhere. So anyway, so this is a ring with identity where identity is Eij, where let's see what Eij is. Eij is equal to 1 if I is equal to j. In fact, this will make all the entries at the diagonal 1, and Eij is equal to 0 if I is not equal to j. So this condition will put zeros elsewhere. So 1 at the diagonal, 1s at the diagonal, and zeros elsewhere. So finally we note that this particular matrix is, so finally we note that M and R is a ring with identity where I is equal to this particular thing, and this can be verified very easily. Its structure shows that this is multiplicative identity. So M and R is a ring with identity. So having established that, let's make a simple remark or note that MNR is non-commutative ring. This is not commutative ring, this is non-commutative ring. Commutative ring, and you know the reason, because for two matrices A and B belonging to MNR A multiplied with B is not equal to B multiplied with A in general. It may happen in some particular case, but in general this is not the case. So MNR is a non-commutative ring. So we have established that MNR is a ring with identity and that this is a non-commutative ring. So having done that, let's come to a very important concept in ring theory, and that is concept of zero divisor. Zero divisor. Zero divisor. So before going to definition, let me give you an example. We know that Z6, this is 0, 1, 2, 3, 4, 5 is commutative ring. In fact, is a ring. I have just written a commutative, but anyway. So we know that Z6 is a ring under binary operations, addition modulo 6 and multiplication modulo 6. And we note that in this ring 2 is not equal to 0. We know that. Note that this means 2 is not congruent with 0 mod 6, which means that if we divide 2 with 6, the remainder will not be 0. So this means we write 2 is not equal to 0. Yeah, 2 is equal to 0. Anyway, in fact, this means this thing. So we know that 2 is not equal to 0, and in the similar way, 3 is not equal to 0. 3 is not congruent with 0 mod 6. But when we multiply 2 with 3, this result is equal to, you know that this becomes 6. You divide 6 with 6, remainder is 0. So 2 multiplied with 3 is equal to 0. In this ring, let me clear it. This means 2 multiplied with 3 is congruent with 0 mod 6, which means if we multiply 2 with 3 and divide the result with 6, remainder is 0. So what we have noted that in this particular ring, 2 is not equal to 0, 3 is not equal to 0, but their product is equal to 0. If we multiply these two non-zero elements with each other, we get 0 element. Note that this does not happen in ring of integers. If you take an integer say 2 and an integer 3, in the ring of integers, 2 multiplied with 3 is not 0. You know that very well. But in this case, 2 is not equal to 0, 3 is not equal to 0, but their If we multiply them with each other, then result is 0 in this ring. Therefore, 2 and 3 are 0 divisors. Therefore, 2 is 0 divisor. Similarly, 3 is 0 divisor. 3 is 0 divisor. So let's come to formal definition. So definition goes as follows. So let R be a ring, then let R be a ring, maybe with identity if you like. Mostly rings we consider are mostly with identity. So let R be a ring. Let's write it with identity. I have written it in bracket just to be careful. So let R be a ring, then an element. An element A of this ring R is called 0 divisor. Important condition is A do not have to be equal to 0. Then an element A belonging to R, A is not equal to 0, is called 0 divisor. Is called 0 divisor if there exists this definition of 0 divisor. If there exists an element B belonging to R, which is again not equal to 0, such that if we multiply A with B, result is equal to 0. Or maybe if we multiply B with A, result is equal to 0, because we have not required that the ring is commutative ring. If any one of these two conditions hold, then A will be 0 divisor. So a non-zero